So hi everybody. Again, my name is Nick Ichien, and I'm a grad student at UCLA. And in the second talk, I'm going to be talking about generative inferences and sort of sentence completion problems, and I'll be comparing two kinds of computational models. This is joint work with Angela Khan, Hongjing Liu, and Keith Holyoke. Okay, so people are often able to use their prior knowledge to generate new ideas or contextually relevant completions to phrases like the one here. And in this talk, I'm going to compare two kinds of models aimed at reproducing this ability. I'm going to distinguish these models in terms of their assumptions about knowledge representation. So the first kind of model employs verbal association over a unified representational space, captured in feature-based models of semantic cognition and distributional semantic models. The second kind of model assumes a representational distinction between entities and relation that's captured in semantic networks as well as analogy models. And in this talk, I'll aim to clarify which of these approaches better characterizes human generative inference. And to do so, I'll compare models of each kind to their performance on short relation completion problems like this one, as well as slightly more elaborate analogy completion problems like this one. So to implement the verbal association approach, I use Google's BERT model that was pre-trained on sentence completion problems, formerly identical to the ones that we'll discuss in a bit. And then to implement the relational reasoning approach, I introduce a new model that operates over vector representations of word meanings, and relation representations acquired by a relation learning model, BART. I'll quickly describe how BART works, and this is the same model that I referred to in the previous talk about recognition memory and relation representation. So what BART does is it uses supervised learning to sequentially acquire representations of individual semantic relations. And specifically, it learns weight distributions over lexical features of word pairs that best discriminate between positive and negative examples of that relation. And it'll sort of use different sets of positive and negative examples for different relations that it's meant to acquire. And so to implement BERT, the verbal association approach, we use the same language modeling task that it was trained on, where it's just given a phrase with a word that's masked, and its objective is to just predict the word that is masked to complete the incomplete phrase that it's given. And so for this particular input, Robin is a kind of, some of its completions include game, drum, stone, and puzzle, and tree. And then to implement BART Gen, we provide a word vector C and a relation R learned by BART, and estimate a word vector D using the inference shown here. The prior term follows the multivariate normal distribution conditional on C, and it reflects this assumption just that C is associated with D. The likelihood term follows a logistic function, and it encourages estimates of D such that D and C together form a good example of the relation R. So in this case, it's generating a estimate of the answer D such that Robin and this generated D form a good example of the relation is a kind of. So for this particular problem, BART-Gen produces much more sensible responses than BERT and more human-like responses. And so what we did to explore this result more systematically is we compared model-generated responses to those generated by a sample of 100 M-Turkers to complete sentences generated out of these word pairs and phrases expressing the relations. The word pair stimuli were drawn from 4 different classes of semantic relations from a larger data set that I'll discuss in the next section. Just for this particular simulation, though, it's important just to know that people generated completions of these sentence completion problems. And here's just some of the responses that people generated for 2 particular sentences that were generated out of the same word pair, just masking which of the words in that word pair people were meant to complete. So when asked to complete the phrase bread is made out of what, people generated fairly sensible responses: wheat, flour, dough, yeast, grain, and gluten. On the other hand, when asked to complete the sentence, what is made out of flour, people again generated more pretty sensible responses and more convergent responses. Most people responded completing that sentence with the word bread, but people also generated completions including cookie, cake, tortilla, wheat, etc. And so we had each of our models, BERT and BART-GEN, complete these same kinds of problems, but we sort of had to change the input to the models to sort of fit their modeling approach. So for a given word pair here, bread, flour, for BART-GEN, what we did is we provided a given word vector and then took a particular relation representation that was learned by that prior relation learning model, BART. And its goal there was to generate the completion of that relation. On the other hand, for BERT, its input was pretty similar to the one that we gave to human participants, where we just provided a phrase with the word that we wanted the model to generate as masked. And here's just another example. Okay, so what I'm going to show you here are actually median rankings of each model's response for the most frequent human-generated response. So for a given sentence, we just took the most frequent human-generated response and looked among each model's set of ranked responses to see where the most frequent human-generated response was placed among each model's ranking of the most plausible completions of a given problem. And so here, it's important to note just that lower performance or lower ranking means better performance. And so I've just split up the median rankings according to the relation classes that each word pair was meant to fall under. And so here you just see that across each of the relation classes that we sampled, BART-GEN is producing more human-like performances. Its ranking of the most frequent human-generated response is much lower than that for BERT. And so we went on to conduct a larger scale evaluation of our models, and we used this data set of 1,580 human-generated word pairs, and each of these word pairs were generated as examples of one of 79 semantic relation subtypes, which were all falling into one of 10 relation types. And I provided each of these relation types here, as well as some examples of each. And then for one particular relation type, here are the sort of relation subtypes that fall under that broad relation type. Again, this is just to give you a sense of the data set and the different relations that are contained in it, as well as examples of the word pairs that are meant to instantiate each. And so here I adopted the same approach to plotting results. I computed the ranking of not the most frequent human-generated response, but the ranking of the word pair completion within this data set. So again, lower rank will indicate better performance. And what I did was I actually split up performance by which particular word within a word pair that each model was asked to generate. So GW1 means that the model is generating the first word of a given word pair, given the relational phrase, the relation, as well as the other word pair in that word pair. And then GW2 means the model is generating the other word pair given the first word, or the other word given the first word of that word pair and its relation. And so here we're just seeing BERT's sort of ranking of the correct response broken down according to which word it's generating. And here's BART-GEN. And just across all of the broad relation types, we're seeing that BART-GEN is generating more correct performance, or generating a lower ranking for the correct answer than is BERT. And important to note here, just the like a magnitude of the difference here. The y-axis is presented on a log scale. So here it's looking like BART-GEN's doing pretty well. It's outperforming this like big model BERT, right? But given that BART-GEN operated on explicit representations of relations for the particular relations featured in this task, these problems definitely favor BART-GEN in sort of allowing it to generate more correct performance. And so in the next simulation, I'm going to test both models on analogy completion problems. And importantly, these completion problems feature semantic relations on which neither model has been directly trained. Okay, so this is an example of one of the analogy completion problems. And to implement that, this sort of analogy completion in BERT, we just adopt the exact same approach that we did previously, sort of phrasing these analogies in terms of a natural language sentence. And then for BART-Gen, we incorporate a slight extension of the approach that I detailed previously. So for these problems, there's not a particular relation that we're assuming that BART-Gen has in order to complete its the phrase that it's given. So what we do is we actually have BART-Gen generate a different response for each of the relations within its sort of relational knowledge, within the set of relation representations that it previously acquired. And then what we do is we compute the relation vector for the AB terms, the first two words, or the source pair of a given verbal analogy. And we use the values of that vector to scale the set of word pairs and compute a weighted average for BART-Gen's response here. And so in order to test these models on these analogy completion problems, we used a data set generated by Adam Green, and we collected, or we re-examined some data that was collected by in a report in a paper by Josh Peterson and colleagues. And these analogy completion problems consisted of near analogies where the A and B target pair were semantically associated with the C and D, the A and B source pair was semantically associated with the C and D target pair. And on the other hand, far analogies consisted of A and B source word pairs that were semantically distant from the C and D target word pairs. And so here, again, the plot is going to be the same, where I'm plotting the median ranking of each model's responses compared to the most frequent human-generated response from the Peterson et al. Data set. And again, here we see that BART-Gen is producing more human-like responses, or a lower ranking for the most frequent human-generated response across these analogy problems. And so the general takeaway here is across both relation and analogy completion problems, a model operating over relation representations outperformed a non-relational model in approximating human responses. So here the theoretical conclusion is that distinguishing between relations and lexical features proved helpful in reproducing human generative inference, at least on these small completion problems. And so that's all I have for this talk. And thank you to my co-authors and for you for attending.